that seems pretty good.
That's awesome. I was like,
Yeah.
That's cool.
Yeah, it's more about being consistent with yourself for this one, too.
You're totally good. I saw that one.
Yeah, I saw the computer and I was like, oh. Apologize.
No, it's all good. I thought it was funny. I thought it was funny. That describes it. Fantastic. I mean, I've got, it's not, for me, it's just time because these two, I Can I try to access it? I'm on the RC server. Yes. I'm writing.
Oh, yeah.
So kind of an overview. On it. What? No. Yeah. So it's like I tried to.
All right, let's go ahead and get started. And so let's talk about plan for this week. So on, have you guys seen those memes that were like, I was going to get my whole life in order, but then we sprang forward? So that's pretty much how I feel, because if I had just had 1 hour, so I have like everything graded, it's just nothing made it into the grade book, so that also includes your quizzes. So I did not get even 15 minutes or anything to put grades in, so I need to do that for chapter 18. But then I started thinking about, well, we still have chapter 19 and 20 quiz, and there's not a lot of turnaround. So my thoughts for that would be, I could give you our chapter 19 and 20 quiz as maybe like homework or something, and then probably in class, so we'll see how far we get with acids and bases. This can be kind of a dense chapter. And so then we'll do the lecture, and then after lecture on Thursday, we'll probably do like a trade-in grade quizzes, or if people need to finish up, you know, talking with partners for answers. But then we could do a trade-in grade, you know, like you did in high school or whatever, just so I can have some grades for you guys, hopefully easy quizzes. And, you know, again, you can take them home, collaborate, whatever. But I just want you to see the quizzes so you have practice for your final exam, and then I'll probably steal some of those quizzes or test questions from your quizzes and put them on your exam. So I'll put those out. So I have them all here. Actually, I'll just go ahead and pass them out. So let me pass them out to you. we have chapter 19 and chapter 20. So like I said, you can do those for homework or start looking at them. Too many papers. And then of course, don't forget that we have our lab exam today, or whenever your lab is. So either today, Tuesday, or of course if you're on the Thursday section, I will see you on Thursday for your lab exam and checkout. And you also get points for checkout as well, so don't forget to check out and clean your glassware just like last time. And then papers due on, I believe, Sunday, right? So probably we'll say 11:59, so Sunday.
I thought it was Thursday.
Oh, Thursday.
I seen the 14th.
I thought it was the 17th, which whatever the 17th is. You can turn it in on Tuesday. That's fine. So are we going with Tuesday? We'll say Tuesday. So that would be the 19th. So 11:59. So try to have it in before then. Ideally, the weekend is also good, so I can start. Either way, whatever is easier. So if there's not an online slot, there should be a separate online slot. If not, just maybe just hand it to me in person. That'll be easier. So paper copies are preferred. Otherwise, you can email them. Because I like paper, so I can like scribble on it and write a question mark or whatever. All right. Any other questions or anything? I do. So I do have some labs, so I'll try to hand those back maybe while we do some examples, because I have things that I graded but didn't hand back to people, but then I also have things that I have graded. I think yours is part of those piled, but they didn't get in the grade book. So yeah, I got to get things back to people. All right, let's start this chapter though, because it is a big one, like I said. And so first we'll start off with just our general properties of acids. And see, you may know this, right? I'm sure you've eaten some lemons in your day or some sour acids. And so acids have a sour taste. And we can also think of like citric acid, or so that's like in candy. Oh, question.
I'm sorry, real quickly. Are these quizzes, what do they do?
We'll go over them on Thursday, like towards the end of class. So if people need like a few minutes, you know how we take our quiz. We'd probably take like maybe 10, 15 minutes if people need to like, you know, check some answers, and then we'll grade them on Thursday. And so if we've had some candy, citric acid is usually used in candy making, so this is a powder we have in lab. And also malic acid, so this is also derived from fruits. And so the other acids as well, tartaric acid. And so all those, obviously, again, make candy sour. And then we've seen that acids can also dissolve metals. So just think back to like our HCl and magnesium and what happened there. And then, of course, they neutralize bases. And again, that's why we have our large citric acid powder. And then we can change blue litmus paper to red. And so now we're just comparing some of our simple acids. So hydrochloric, right, hydrofluoric, hydrobromic, versus these organic acids, which will take a closer look at the organic acid structure. And so here's just a list of common acids. And so like we said, there's hydrochloric. So this is used in like metal cleaning and ore refining, so like releasing metals. And also is your component of your stomach acid. So of course, right, you probably know your stomach is acidic, and so it has hydrochloric acid in there to help break down your food. And then sulfuric acid, so that is used in fertilizer and explosive manufacturing, and then it's also a component in batteries, also used in like electroplating. Nitric acid, so also used in fertilizer and again explosives, so nitric is good for explosives and then can be used in other productions. So acetic acid is just vinegar, so of course, right, used in food preservation and pickling, and then also used in rubber and plastic manufacturing. And then citric acid, so this is the common one used in candy, but again, you might find other variations in candy, and can also be used to adjust your pH. Probably find this in maybe 7-Up and stuff like that. And then we have carbonic acid. So we mentioned carbonic acid just comes from carbon dioxide dissolved, and we can go into, right, everything's a huge equilibrium with our carbonic acid and our ocean, and of course all the limestone in the ocean. And then hydrofluoric acid, so you might be familiar, so that's used for like glass frosting and etching. I'd also add to this chip production, so often used in like research settings too, to like clean your chip, prepare your chip. And then our last one, so phosphoric acid, once again fertilizer, but then it's also a huge component of biological buffers and then beverage preservation, so often soda has a little bit of phosphoric acid in it as well. So then if we look at our organic acids, so now we can look at this group in more detail. And so we say that organics have this carboxylic acid group, at least for the most part. And so our carboxylic acid group is this COOH, but I like writing it out. So it's one carbon double bond to oxygen, and then the other is single bonded to oxygen and a hydrogen. So our OH group. And so this proton here is the what we call acidic proton. And so that means it's going to be susceptible to deprotonation. And let's kind of look into why. And so we just take our group here, and let's just play. So I'll use water as my base. And so that means that water can come along potentially, pluck off this hydrogen, and then we'd be left with this species, plus now our carboxylate ion. And so notice, right, the electron. So now we have this structure. But why this is so favorable is that it's resonance stabilized. And all that means is we can draw resonance structures. So we have our ion, but then we can say, well, what if we move these electrons down, create a double bond on this side, move that up. And so now we get our resonance structure. So just moving our negative charge to the other oxygen. So now we have our double bond down here. And so this is why this is so stable and why it's acidic, is because we have this resonance stabilization. So now this negative charge is delocalized over these two oxygens. And so that is favorable. So that's why, again, we see that. And that's why this is our acidic proton there. And so again, we'll see this in our organic, so acetic acid, citric acid, and like I said, malic acid, and many others. All right, switching to bases. And so hopefully you guys haven't tasted too many bases. And so bases often taste bitter since they're poisonous, again, in general. And so do any of you ever get your mouth washed off with soap anymore? Or does that still happen? So some people, yeah, so then you know, right, that bitter taste, so that's why they do it. So it tastes bitter, and then maybe you even notice it felt slippery. And of course, you probably know that just from like soap feels slippery. And maybe if you've touched bleach, but not that I recommend you try to touch bleach. But, you know, if you touch some bleach, that also gets that slippery feeling, or sodium hydroxide has that same weird feeling. And of course, bases can neutralize acids, and if we were using our litmus paper, we would choose red litmus paper, and it would go to blue. And so we can see our household chemicals and our Maalox, so not a household chemical. So, right, there are a few we can ingest. Milk of magnesia for our bases. And so now we have our list of common bases. And so if you look, so both sodium and potassium hydroxide are used in soap manufacturing, so they're used pretty interchangeably. Just again depends what base you prefer. And then they can also be used in petroleum processing, plastic manufacturing, cotton processing, electroplating, and then batteries. And then we have sodium bicarbonate, so of course we know that as baking soda, so that's often used as an acid, or they use it, and again like those candies, so like the Zotz candy, I believe they use sodium bicarbonate in there as the base to get the nice fizzy reaction. And then sodium carbonate is also used, and so this can be a water softener. And then we also have ammonia. So ammonia is an important base, and again used in fertilizer and explosive manufacturing, but then also definitely fertilizer. So I just star fertilizer for ammonia. Oh, I forgot to mention, did you guys see that for the Medford water, they're adjusting the pH a little bit? Yeah, so the Medford water, I don't know if you guys saw, because they're making it slightly more alkaline. And so their hope, so going back to acids versus bases, so right, we just said that acids dissolve metals. And so if you have a slightly acidic water, and I can't remember now the pH, because it was pretty subtle. It was going from like 7 to like maybe 7.4 or something, so pretty small. But so, right, we just said, well, acids dissolve metals. And so that's what happens, right? If your water's too acidic, eventually it can be leaching, metal ions, especially from your pipes. And so the Medford water people decided to adjust it a little bit, make it slightly more alkaline in hopes to prevent some of that metal from coming off as much. And so they actually just use sodium hydroxide to adjust it. Yeah. I mean, it could potentially if you're like removing out some ions, yeah, because it would kind of depend. It's probably pretty subtle, but right, just thinking about it. So if they use a sodium hydroxide, and then depending on your filter, if it manages to filter out some of those hydroxide ions, then it could, change it a little.
But it would also probably filter out the harmful metal ions, which are the reason that.
Yeah. Yeah, and I mean, there's, you can really go down the rabbit hole with water chemistry too, because then it's like, do you want a water softener too for your place, and what does that entail, maintenance and all that, because that is a concern with our water now, since they're making it slightly more alkaline and they are using sodium hydroxide, you may see more particulates, and it will be slightly harder. Again, I don't know how noticeable it is. I think the change already happened, but it's kind of interesting to at least think about. And if you were, that's something that chemists can do and be employed by, right? That's very important, to be testing the water all the time and checking for it. So yeah, it's kind of cool. But yeah, personally, I was honestly surprised they just used sodium hydroxide to change the pH. I would have thought they would have picked something milder like a carbonate, but yeah, pretty interesting. All right, so now let's go over this hydronium ion. And so let's just kind of break down what this is saying. And so half of what it's saying, and well, let's go over this. This is a little bit later in the text, or in your chapter. But water can do what's called autoionization. And so basically, if we have two water molecules staring at each other, there's a potential that one of them can act as a base. And so that's what happens. And so we could have let's just say this one attacks. And again, notice action always starts at the electrons. And so then we would make hydroxide and then plus hydronium. And so that's what's shown here. What can also happen, so we've talked a lot about disassociation, so talking about HCl, and we often just write it like this. And this is kind of, again, like an abbreviated understanding. And we just want to highlight that what's really happening is that they don't just split apart, because the truth is we can't have just a naked proton floating around. So what really happens, again, instantaneously, is that as soon as your HCl goes in there, then your water would pick up that proton and really make hydronium, since we're not, again, we won't just have a H plus floating around, so that would be too reactive, so then it really forms this species. And of course, there's our chloride. This part is the autoionization, but we will go over this again. But all I'm showing is just like base attacking H plus. And so now let's get back to the text of what we're trying to show. And so all we're saying is that chemists are pretty much lazy. And so even though we may mean H3O plus, chemists always tend to just write H plus. But then we have to know that H plus truly does not exist in solution. So again, they would be so reactive that they can't exist. And so that's why, again, I drew out this mechanism showing how HCl would enter in, and then water would be, boom, attacking that proton, and that's what drives our dissociation. And again, equilibrium lies all the way to the right with our strong acid dissociation. And so again, use interchangeably of H plus versus hydronium. So just keep that in mind for this chapter. And then again, watch out. So if you look at other resources, especially in the acid-base chapter, I don't know what it is, but I've seen reliable chemistry sources have this H plus like attacking. And that I would say is absolutely wrong. So you should never have H plus initiating anything. So action always starts at the electron. So just keep that in mind. So be warned, you might see bad mechanisms out there. So especially if you continue on to OChem, you always want to start your action at the electron. That's what drives everything and drives your mechanism. All right, so now let's go over kind of our definitions of acids and bases. And so we'll start with the Arrhenius definition, which I assume most people are familiar with, but we'll go over it. We'll talk about Bronsted-Lowry and talk about where the Arrhenius fails. And then we don't talk too much about Lewis in this chapter, but we'll go back and look at some examples after we talk about the other two. And so our Arrhenius theory is, again, the simplest. And so acids are just anything that produce H plus ions in solution. And so that's any of our strong acids that dissociate. And we'll link back to HF. So HF, right, still produces ions in solution, but it is a weak acid. So there's some sort of equilibrium. But again, still H plus, so that's easy enough to see. We can add nitric to that, right? All the organics kind of fall with that. So vinegar. So all that seems pretty simple. And so same thing with bases. So then bases are anything that produce hydroxide ions. And so I would add to that, right, magnesium hydroxide, calcium hydroxide. So all our hydroxide compounds, so ionic compounds containing hydroxide. So those can all fit there. And again, they disassociate, just like we see with sodium hydroxide. So fairly simple. And then, so then we have our acid-base reactions. And we can think back to first quarter of just, again, what's really driving those reactions. So let's just take something really simple. So hydrochloric acid plus sodium hydroxide. And then obviously, right, this was a double displacement. Again, thinking back to first quarter. So we do our double displacement reaction. Then, of course, we make water. And so it just reminds us that here. So H and OH make water. And then we make our salt, which is still aqueous in solution. And so I just want to remind you that, again, it's the water formation, right, that drives this reaction forward. So we're making water, and so that's what keeps driving that equilibrium. So, right, not the salt formation, since that's just ions in solution. And so blah, 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 so we saw that. So that's good. And so, of course, you can probably start thinking of some problems. And so we are aware that ammonia is a base, but, right, this doesn't explain how. So there's no OH ions in ammonia here. So how do we make a base? And then we also don't explain how sodium carbonate or sodium oxide, so these as well dissolve in water to form basic solutions, even though they don't contain hydroxide. So that's a problem. And then it doesn't tell us why CO2 can dissolve in water and form acidic solutions, again, even though there's no H plus ions. And so now we need a little bit more expansive theory. So now this brings us to Bronsted-Lowry. And so the definition still encompasses our Arrhenius ones, but now we've changed the definition slightly to be any reaction that transfers a proton is called an acid-base reaction. And so that means that an acid is defined as a proton donor, and a base is defined as a proton acceptor. And so generally the base has some sort of lone pair of electrons, which means, right, that's why it goes ahead and grabs the proton. And so that's my slight issue with this definition, right, is that it's saying that it's a donor, but you always have to think of action from electrons. I feel like you skipped to the Lewis base. Yeah, because the Lewis definition talks about sharing electrons, but we'll look at this because this is more specific, right? So this one isn't just like one electron coming together. We'll see that it's a dated bond, but yeah, I don't want to jump the gun. But under this definition, it should just be a proton transfer. So I'm not sure what reactions you're thinking about, but any sort of proton transfer is usually just acid-base reaction. That being said, right, proton transfers happen all the time, but it's still just acid-base in a lot of sense. And so then we kind of bring into this new terms, which are useful. And so then we have our HA acid here, plus our base. And again, right, we notice they drew some lone pairs on there to try to hint. And then when this reaction happens, so of course, right, the acid is going to give up its proton. And so now minus a proton, it becomes our conjugate base. And then our old base now becomes our conjugate acid. And so notice how it picks up that proton there. And so now we can see this. We'll start off with just a simple example. So looking back again at our water, and I'm just rewriting it to emphasize the mechanism, since you want to be comfortable with that. Again, imagining, right, our base has those electrons, so it's going to go ahead, it wants that proton, and now we make chloride, and so now we've made our conjugate base, and again we can compare. So now we have our conjugate acid-base species. So we have our acid, right, HCl, and then the conjugate base pair, chloride. And so notice, right, again, they just differ by a proton. And then so same thing, so now our base becomes our conjugate acid. And so now I'm just rewriting out our hydronium. And could have just seen H plus if someone was being lazy. So again, just watch for that. And so now we have our conjugate acid, and then again our acid-base pair, so water and hydronium there, differing by 1. And so now if we look at our bases, and so now this helps answer our question for how is ammonia a base, and so let's draw this out. So we can start with our Lewis dot structure. And so again, right, this is where our Lewis dot structures are still useful and powerful. And so we start with ammonia, again, our lone pair, so 2 electrons, and water. So you're already getting a sense that water can act as an acid or a base depending on the situation. And so in this case, it will be our acid. And so nitrogen now attacks our proton, so those electrons go back to our oxygen. And then they put equilibrium arrows, so we haven't quite gotten there yet in this chapter, but ammonia is a weak base, and so that's where it has that equilibrium, right? So not all of it will fully disassociate, so we'll get into the math. I know you guys are eager for the math, but that's why we have our equilibrium arrows. So then some of it forms our ammonia here. And so they just wrote NH4, but I'll write it out. Here's our nice little structure. And then, of course, our conjugate base. And then again, just note your base, acid-base pairs. So we have ammonia and ammonium, right? So again, they just differ by a proton. Then we have water. So now water's acting as an acid. It lost its proton. And then water and hydroxide will be our acid-base pair for that one. Questions so far? And so again, we'll be using our Bronsted-Lowry to kind of help us, especially with the next chapters and setting up our equilibrium. So again, we can just see our equilibrium and write some Ka expressions. And then we also want to practice, again, we'll kind of get into this a little bit deeper, but how does a reverse reaction work? So now you take your conjugate base, and then we'll see how it reforms our acid species. And so again, that's something that we want to identify is our conjugate acid-base pair. And the key point, again, I'll just highlight, is they're always different by 1 proton, your acid-base pair. And so we'll do the practice, but I'll give some warnings for the future. So oftentimes you'll try to be tricked, so you'll give some scenario of like which are your acid-base pairs, but which one doesn't belong out of those 3? So the first one, so exactly. So watch out for that. Is again, I'll often try to trick you or problems. That's a concept that is tested all the time. Is can you identify the difference? And so yes, this is a 2-proton difference, so that's not appropriate. But everything else, right, is just 1 proton. And so those would be appropriate acid-base pairs.
Especially when you word it acid-base pair. Oh, that one's H plus and that one's hydroxide. They must be by acid.
Yeah, yeah, this one often tricks people, exactly. So just watch for that. All right, try the practice problem, or try both of these. So we have 2 reactions. So first one is sulfuric plus water gives us hydrogen sulfate and hydronium. So identify your acid base and then conjugate acid base. And then try that again with hydrogen carbonate and water, making carbonic acid and hydroxide. So looking at A, so which species was our acid? Where we get, so H2SO4, so I think that looks good. And so we can tell that, right, because it gives up a proton. And so if this is our acid, what does that make? Water. So our base. And so now it follows. So now if water was our base, what's hydronium? So now this is our conjugate acid. And again, right, it has 1 more proton than our base. And then what does that make this last species? So exactly, so our conjugate base, and it should have, again, 1 less proton compared to our acid. Questions on A? So then B, let me write that out. And so now what do we get for water? So let's see. I don't know if it's our, because we just want to call these acids or bases. So then, so if water is our acids, let's see if that makes sense. So let's see, it looks like it's losing a proton, so that's a good key, so yes. And so this is our acid. I'll go ahead and label this, right, our conjugate base. And so if this is our acid, what does this leave? Our hydrogen carbonate species, base. And again, maybe we want to write this one out so we can see. So we have to start off our carbonate. So this one is a little weird because we have to figure out what to do with our proton. So carbonate. Try something attached like that. CO2. And so we have our hydrogen carbonate ion floating around, so negative charge on our oxygen. And so yes, we can see how it's going to act as a base and then pick up that proton. So again, making our hydroxide. And then what's this carbonic acid now? What can we call it? Conjugate base, conjugate acid. So now this is our conjugate acid. Questions about that one?
I was wondering, maybe I missed something. What exactly determines which set is the conjugate set, which is the Bronsted-Lowry set?
Maybe. So these are all just related to like the Bronsted-Lowry, right? So it's all about just identifying which one's your acid or your base, kind of depending on whether it's losing a proton. And then so if it loses it, right, that just means it's a conjugate base. And this is all, again, just based off of the Bronsted-Lowry theory.
And for the dynamic equilibrium, is it just something left to right with a certain forward direction?
So like going backwards, you mean the carbonate and hydroxide, or?
Well, I guess I was wondering, we determined that, on the right side in this specific instance, it's the base of the acid, and then on the left side, it's the conjugate base of the conjugate acid. And I was wondering, I can kind of see that for the first one, it's moving in the forward direction, as a new compound in there, but for the second one, it's a dynamic equilibrium. I was wondering if that changes things, or if they still just go in the forward direction with forward direction reactants being acid base, and then forward direction products being conjugate acid and conjugate base.
Yeah, so I think I follow. So if I follow, really, we just say who's ever the reactants are our base and acid. But to kind of follow with what you're saying then, right, well, then we can take carbonic acid, H2CO3, and then react it with water, and then that would be a new sort of thing. So is that what you're saying? So then this would now be our acid, right? This would be our base, and then, right, then we could reform our hydrogen carbonate, right? So then we're left back with this. So then this is now our conjugate base, and then we'd make hydronium, right? So H3O plus, and so now this becomes the conjugate acid. So it all depends kind of how you're looking at it, I guess, like what way you're starting from. Does that help clarify? Yeah, so it all depends on your scenario. So whatever we're looking at on our left side, we'll always just kind of figure out, is that an acid or a base, again, relatively speaking. And then kind of our product side formally, we'll figure out, right, then they have to be conjugate acid, conjugate base, but yeah, we'll keep seeing that we can, right, reuse our products as in reactants somewhere else, and it's good to keep in mind, and I think it's better to write them out as like separate processes sometimes, because there's like small subtleties. All right, so before we move on, let's go back and at least discuss, well, what fits in the Lewis definition. And so again, it's not covered in this class, but once you get more, especially into like research, they're always going to be referring to this definition. And so the Lewis definition is now the most expansive, and it's based on electron donors and acceptors. And so the classic examples to this are ammonia and boranes. And so I picked kind of the two simplest ones. So we have ammonia and BF3, but let's write it out better. And so ammonia, we remember, has our lone pair, and BF3, so we remember boron has 3 valence electrons, and so it only has 3, right, electrons for bonding, so it typically only makes 3 bonds, but because of that, it's electron deficient. And so again, in research, they use a lot of these nitrogen-boron complexes to create what's called frustrated Lewis pairs. And so the thought is that you want to get 2 things really close to each other that want to be an acid-base pair, but maybe your structure, your ligand, your compound holds them in such a way that they can't quite react, and the thought is for them to do something cool, aka some sort of catalytic cycle. So lots of research in this area, but again, the key point is that, well, boron probably wants some electrons, and so they can form what's called a dative bond. And so often, if you are looking at a dative bond in literature, they do try to indicate it with this arrow to show that in this bond, nitrogen is donating both electrons. So they probably won't draw the electrons, but it might be something like this, and then showing that it's complex to BF3 or any other sort of boron compound. And so this would, of course, be our base then by our definition. So ammonia is still our base, except now a base is defined as an electron donor. And then our acid is defined as our electron acceptor. So boron in this case, of course, is our acid accepting electrons. So again, we probably won't see too much of this more in this class, so we'll kind of go back to the Bronsted-Lowry definition. But again, if you start looking around in literature, there's probably a lot of literature on this frustrated Lewis pairs, and they often, again, use the Lewis definition in other levels, so especially like CHEM 2, you'd be looking at who wants the electron and who is accepting the electron. So it's good to at least start thinking about this definition. And you may want to write this out as your little cheat sheet, because sometimes it gets a little confusing, right? So acids are donating protons, but then they're accepting electrons. So you just want to make sure you have that kind of straight in your head. All right, this may be a good time to take a little 10-minute break, and then we'll go back into our strong versus weak and talk more about equilibrium. So reconvene in 10 minutes.
which makes me feel like a good girl, but
I mean, I think a lot of currently with this,
yeah, yeah, that's what it seems like. I remember the cousin asked, he's like, how do you do service? I'm like, yeah, wait, how do you do a service in a girl? And he's like, we'll get to that, and then we never did a service in a girl. I was like, okay, well, I guess I didn't answer the question, but I didn't eat that.
I was actually talking about there's so much stuff
Yeah, yeah, yeah. The like Simpsons stuff. That doesn't seem very good. You do the same goddamn fucking thing. Oh my god. Yeah, I take that pretty easy, so. Oh, and it does the mid end Simpsons. Okay, okay. Something like that. Yeah, you're like, nah, this is hopeless. I'm just gonna. Oh, you just need to plug in the. Okay. And then for the one where you did the function, you plugged in, that one just goes live on program, so whatever it is. Yeah, I've done this. Oh, yeah. Oh, yeah.
So I'm getting this, the equilibrium constant K, and it's multiplied by a coefficient of 2. I know the reverse, and it's a reverse reaction as well. So I know it's the reciprocal. So I was thinking it's the 1/2 K. But then I saw, yeah, because then I saw in my notes that it had like K1 equals K2 to the n. So it would be to the power of the 1/2 rather than.
Well, yeah, be the power of the 1/2.
Oh, okay, so like the square root.
Yeah.
So I think that's the same thing. My brain is fuzzy.
Yeah.
Thank you.
I'm surprised you're not.
Yeah, no, for real, like actually, you spend an hour writing an email. It's the simplest thing you've done in your life.
All right, let's come back. All right, so now we're first going to differentiate between our strong acid versus a weak acid or a base. And so again, the strong just refers to complete disassociation. So it has nothing to do with how dangerous it is.
Is there a different word that you would use to describe how dangerous it is?
Yeah, I feel like there should be a word, but there isn't, yeah. And so anything that is a strong acid, so that means it's a strong electrolyte, so it's going to completely disassociate. And so same thing, so then we'll compare, so we'll look at some weak acids, and again, what differentiates it is only part of it is ionized. And then, of course, right, we'll have our equilibrium, which we'll be able to quantify. And so again, strong base, that's usually, right, our ionic compounds for our strong base. And then we'll find that our weak bases tend to be ammonia or ammonia-based complexes, so like amines. Like, now will be the time to talk about methylamine. So this usually comes up, although now I don't know if people have watched Breaking Bad anymore. But yeah, so that's methylamine, the important base, right, that they hijacked from the train. But amines are wonderful compounds, so it's pretty sad that this is now a regulated substance. And so again, same thing, there will be an equilibrium. And, yeah, they're either going to be like an amine or ammonia. That's, yeah, those are the ones we'll typically see, / I can't think of any other common ones. And so general trends, I want to come back to this statement because this is an important statement, but we'll want to dissect it some more. And you probably heard of it. So the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. But again, we'll dive back into this. And then other general trends we see is so higher oxygen numbers, the stronger the acid. And so that's comparing sulfuric versus sulfurous acid with one less oxygen, so sulfuric is stronger. Same thing with nitric versus nitrous. And in practice, I've actually never used this sulfurous or nitrous, but I'm sure they have some use. And then we find that cations are stronger acids than neutral molecules. And so, right, keep this in mind as well for like other cations. So something that is a cation is typically an acid. And then we find neutral molecules would be a stronger acid than an anion, which again kind of makes sense with our definitions, right? So we said an acid has to be accepting electrons by our Lewis definition, and so that's kind of where that comes into play as well. So, right, if the definition is an acid accepts electrons, then that's why it makes sense, right, that a cation is a stronger acid. And then that means, right, anions are poor acids, but of course would make good bases. Again, thinking back to our Lewis base definition, where we said a base was an electron donor. So just keeping that definition in mind may help us make sense of those trends. All right, let's go back to that statement, because now we have this pretty picture here. And so maybe I should have printed out this chart for you in retrospect. And so if we look at the top here, so the top here are your 6 strong acids. And so you could star these or whatever, so you know, okay, these are the strong acids. So perchloric, sulfuric, hydrogen iodide, hydrobromic, hydrochloric, and nitric. And then, of course, right, these would be their conjugate bases. And let's just think about this. And so now let's start to compare. And we'll go back to our hydrochloric acid. So we said, and I'll just react it with water. So he said it disassociates, so we make hydronium and chloride. And then let's go back to this statement. So it says, okay, the stronger the acid is at donating, the weaker our conjugate base is. And so now in the case of our strong acids, what we're really saying is, okay, this is our conjugate base, and let's just write that down. So acid, so this would be our conjugate base species. And we're saying that this is such a weak base that this can't happen. Because what you're really asking is, can it reform HCl? And so the answer is no. So, right, it can't actually, donate and pluck off a hydrogen from water, because again, it's such a poor base. So, right, this does not happen, so no reaction, right? So no HCl is reformed. And so now let's look at our other weak acids and weak bases. And so the rest of the chart has, again, some examples. And let's look at HF. And so HF is a weak acid. And so let's compare the reaction and what's going on. And so again, now we have HF, which is our weaker acid. Now we're in equilibrium, right? So it makes fluoride plus hydronium, or H+. But now we're saying, so right, HF is not as strong of an acid. And so that means, right, its base, so fluoride compared to chloride is a better base. So we can label our species again. So this is our conjugate base. And so if we were to just take fluoride in solution, so this would even be, let's say you dissolve sodium fluoride, well, that fluoride will react with water to reform HF. So now it reacts, and so then we get HF, and then of course, right, hydroxide here, because I showed it reacting with water. But this shows us the reaction that's going to happen. So again, right, this is why it's a base. That's why I was able to do that. Again, going back to this statement. And so we're saying, okay, well now we have a weaker acid, so yeah, that means its conjugate base can accept that proton. So yes, and that's why any of these, right, can again reform, re-pick up their proton. So they can act as a base. But then I wanted to point out fluoride specifically because this brings up additional safety concerns, which sometimes if you haven't thought about it before, you may just be unaware or not think about it. So this is a danger when either using fluoride salts or if you're doing a reaction that maybe forms a fluoride salt. So if you're trying to get rid of a fluorine, sometimes you make, sodium fluoride or some sort of fluoride salt. And this is dangerous. So you're making this as your byproduct. So you're really making HF then in some small amounts. And so if this was a reaction, you would have to know to neutralize that. So you'd want to neutralize that and get rid of that HF. So I'll just say, like, in a reaction, might need to neutralize. And so that's, again, just something that you'd want to keep in mind as a working chemist is what waste am I making, what am I generating, and then how do I need to take care of that. And of course, you want to neutralize HF since that presents an additional safety hazard. So do we feel okay about this fluorine or this fluoride ion reacting? We'll keep practicing. So we'll keep looking at stuff. Where were we? Okay. That's good. And so now we're starting to get into the Ka. We're teasing it now. And we'll have to, of course, write our expression. But we can already kind of see where this is going to come from, our Ka. So we'll start with some sort of, right, acid, and then it will disassociate to make H+, and then how much conjugate base, and then we'll have some sort of equilibrium expression. So just like before, products over reactants, and again, we ignore water, right? So we remember that from previous chapters. We don't include water in this equilibrium expression since that concentration doesn't change. So then we'll be looking again at this scenario. And so right now it's just kind of telling us our general strategies. So of course our strong acid, obviously the equilibrium is going to lie all the way to the right. So we'll say our Ka is greater than 1. And so we have, again, nearly 100% ionization occurs. And so we mentioned, again, that would be a strong electrolyte. And we use, again, H+ and hydronium interchangeably. And so there are our 6 strong acids again. So have them written somewhere, or again, you can refer to the chart. They're the top ones on the chart. And of course, for this one, right, complete disassociation. So whatever your molarity is of your acid, right, that is equal to your H+ concentrations. Maybe I should write that down. And we'll see this with the pH problems. But basically, if we have a 1 molar solution of hydrochloric acid, right, then we can just easily know, well, it fully disassociates, so I have a 1 molar concentration of H+ ions or hydronium, however you want to call that. So that's all that's saying here. But again, we'll practice with the pH. And so weak acids would then only have a small fraction disassociated. And so again, we saw that with HF. And so just showing you a little visual representation. So some of them, of course, are still complex together, and some have split to make our hydronium and fluoride. And so now this is saying that our weak acid does not equal H plus in solution. So all this is saying is if we had 1 molar solution of HF, right, that is not equal to 1 molar of H plus ions, right? So that's where we have to get into the math, kind of like you did with the lab, if you remember back to the lab, but that's where that comes from, is we have to figure out our equilibrium, right, how much is disassociated, and plug that all in. And so some examples are given here. So ethanoic vinegar, carbonic acid, formic acid. But this is not an exhaustive list. So you do have this chart that kind of shows you more examples of acids. So we have chlorous acid, nitrous, HF, formic, benzoic. So again, a lot of these have the carboxylic acid group. Or some of them just have OHs, and some of these get lower. So phenol is a weak acid. So we'll come back to this. And so then, right, we have to, of course, be given our strength of our acid or our base. And so we'll mainly be focusing on Ka, but we'll take a look at Kb as well. And so our strength is, of course, just measured by determining our equilibrium constant and measuring our pH. And so this first reaction is just kind of showing you, right, your HA plus water. And then, of course, makes your conjugate base plus hydronium like we saw before, so always in that same form. Or in this case, right, we could have our base, like our fluoride, so A minus plus water gives us back our HA, so there's our conjugate acid, and then plus hydroxide. And so we've kind of seen this, right, with our previous equilibrium chapters. So, of course, the further the equilibrium position lies towards the products, the stronger the acid or base. And so I've scrolled through the chart pretty quickly, but then we can look into, again, their Ka constants. And so for an acid, you'll be given your Ka constant. For a base, it gives you your Kb constant for this reaction. And so if we're comparing, so let's compare this chlorous acid versus hydrocyanic acid. And so we're comparing 1.1 times 10 to the negative 2 versus 4.9 times 10 to the negative 10. And so this one, right, is less small. So this would be our stronger acid. And so if we go back to the chart, so I'll skip around for a second. And so if you notice, there's two numbers over here. So there's the Ka, so that's of course our equilibrium. But then if you notice, most chemists, or again, if you go on to OChem, they'll use this term instead, the pKa. And so let's figure out, well, how the heck do we go between those two? And so to convert between those, and so we're about to do a lot of logs. So the negative log of our Ka is equal to our pKa. And so our pKa is really just an easier way, right, to represent our Ka. It's just easier to talk in pKa's. But notice, and so now I'll show more of the chart. So at the top, right, we have the most acidic at the top. So their Ka's, right, are not as tiny, but then their pKa's are lower. So the lower your pKa, the stronger the acid is. And then if you notice, right, so now let's just look at benzoic acid for fun. So that's 6.5 times 10 to the negative fifth. I'll go ahead and pull out my calculator. And so most people shouldn't have issues with the calculator, but definitely check it, because I've had issues in the past if people use like accounting calculators or something, then it's like in the wrong base or something weird. So that's really the only issue that has cropped up. So just double check. So we'll plug this in. So negative log of our Ka, so 6.5 times 10 to the negative fifth. And then yes, that gives us our 4.19. And then so also notice that you add a sig fig. So right, we only plug 2 in, but then once you take the log of something, you add an extra sig fig digit. So now it's 4.1, and then we can round to 3, so 4.19, which is the same answer they had there. So again, just double check your calculators, yeah.
Is pKa different than pH, or is it the same thing?
It is different. They are pretty similar in some ways. So you'll see formulas where like the pH is equal to the pKa plus something, or sometimes there are scenarios where pH is equal to pKa. But yeah, they're kind of all related, but not quite. So yeah, the pKa though is just our measure of our equilibrium constant, truly, right? So it's just our different way of expressing it. Well, like I said, you'll find that chemists generally talk in pKa's rather than Ka's. And so now let's go back to our equilibrium. And so then we have our acid ionization constant. And so we could figure this out. I wrote it out earlier, but again, just re-derive it for yourself. So it was just our reaction, right? Our acid plus water gives us hydronium plus conjugate base. And then we get this expression. So getting rid of the water, since again, it's not part of our concentration expression, leaving us with our Ka here. So again, this should match what we know from our equilibrium, but I would still, write this down. So my Ka is equal to H plus, or again, hydronium used interchangeably, times my conjugate base over associated acid. And so again, like we have seen, so the larger our Ka value, the stronger the acid, right? The more the equilibrium favors the right. And so there again is our table. And so these ionization reactions are also useful because, again, this is showing you what the Ka equation is. And so now this formally goes over the autoionization of water. And so like we were seeing, so in our scenarios, right, water could act as an acid or a base. So it's called amphoteric. So there are a few other substances.
With KB, does it have the same relationship in that, like, if pKb is smaller, then the stronger the base?
Yes. So it would have a similar.
Same relationship?
Yeah. Sorry, I was looking if we do some derivations with KB. I don't have my KB stuff. Yeah, we'll talk about KB a little bit. Because the problem is KB is not quite the same, right? So we could go back. I mean, you're right in that it says, right, how much it's telling you our equilibrium. But it's just that our KB, so right, KB is then equal to our HA times hydroxide over A. So that's KB. But then what's also relevant, and we'll get to it. So we'll keep that in mind, what KB is. And then, so let's look at auto-ionization of water. And this might also help us. And so now we're starting to get to how we even got to pH. So we were saying that water can do this. And so it's only 2 out of every 1 billion water molecules undergoes this ionization process. And so we saw that earlier, and so it's often abbreviated as just a water splitting, but I would say, right, that's kind of inappropriate because we want to have our action coming from our electron. So this is kind of the better way, right? So you want to show your 2 water molecules and the fact that one of them kind of attacks the other one. So blah, blah, blah. And so, right, we're getting into this. So all aqueous solutions contain both hydronium and hydroxide concentrations. And so this is cool. So how we started getting into our pH. And so now we can say that they have equal concentrations. So 1 times 10 to the negative 7th at 25 degrees Celsius. And so now we get into KW. And so now this is saying, this is our water product constant. And so it's saying that these concentrations are always equal to KW. So basically we can take our hydronium and hydroxide concentrations, and they should always be equal to 1 times 10 to the negative 14. And so let's look at a few things. So this actually isn't in here, but since we brought it up, let's talk about it. Because I feel like KB is neglected. I don't really know why. No. Now that we're trying to teach it and talk about it, KB is always neglected. So we had said Ka was hydronium times A minus over HA. And then our KB then, so right, we said that was conjugate acid times hydroxide concentration over A minus. And so what's cool and how we got our KW, or part of how we got our KW, and we should maybe know this. So Ka times Kb is equal to Kw. And so we can do a quick derivation. So what is this? So let me zoom out. And so let's plug this in. And so now I'm just rewriting. So Ka times Kb then. So Ha times OH over A minus. So then we multiply them, and so A minus cancels, and HA cancels. And so this leaves us with, right, hydronium times hydroxide. And so that's where, again, our KW came from. So it kind of skipped to it in our lecture notes, but I was good to at least kind of go back to that. And so our KW is our water product constant. And so again, for our purposes, we are always going to be at 25 degrees Celsius. And so at 25 degrees Celsius, our KW is always 1 times 10 to the negative 14th. So now this is starting to hint at our pH scale. So again, we said, so we found that, our KW. And so often what we'll see, and again, we'll be playing with this with our pH. So as our H plus ions increase, then our hydroxide must decrease so that our product stays constant. And so then we have our basics about acids and bases, basic solutions. So right, well, we said that all of them contain hydronium and hydroxide. Neutral solutions have equal amounts of both. But then we'll find, so acidic solutions have to have a larger concentration of H plus than hydroxide. And of course, basic will be the reverse. And so start off with this. See if you can base it off of these concentrations, thinking back to the neutral. But then we'll kind of tease into pH and how to calculate that. So what do we think about A, acidic, basic, neutral? Try to look at it again. So it should be acidic, right? Because you're trying, and these are kind of tricky because you're trying to compare it to this -1. So is it greater than 1 times 10 to the -7? And so yes, it would be. And then what about B? Acidic, basic, neutral? So basic, so now it's less than 1 times 10 to the -7, so even smaller. And then what about C? So neutral. And so personally, right, I don't really like trying to compare acidic, basic, or neutral with these exponents. And so now let's move on to, well, how do we measure pH? And so you're probably familiar with this expression. So pH is our negative log of our hydronium concentration. And so let's go ahead and plug in A, because that will be easier to see. So negative log of our H plus, so 7.5 times 10 to the -5th. And your pH should be roughly around your order of magnitude. And so, right, we had an order of magnitude of 5, and so we get that right for about our pH, so 4.12. And now that's much easier to tell that that's acidic. And so now we have kind of our fun table of random substances. And of course, if you get bored, right, we have pH paper in labs. You can always knock yourself out. And so stomach acid is generally pretty low, around 1 to 3. And then limes and lemons, right, are all also really acidic. And so, of course, that's why your dentist will, be worried about you consuming too many limes and lemons, so that can wear down your teeth enamel. So same thing with soft drinks and even wine. So all of that can have, right, a weakening effect on your teeth enamel. And then, right, more fruits, so starting to increase in pH, like apples, peaches, cherries. Beer is almost neutral, around 4 to 5. And then rainwater tends to be somewhat acidic, so like 5.6. Human blood, of course, you're aware that's a buffer, so that's kept at a pretty tight pH range of 7.3 to 7.4. Egg whites are slightly basic. Milk of magnesia is 10.5, so of course if you have a stomach ache. And then household ammonia, that's going to be like 11. And then your sodium hydroxide is, of course, 14. Negative log of what?
10 to the negative 7 for pH of water.
I think you have to put 1 times 10. Yeah. And so then we get to our pH scale. So of course, you probably know this, right? It goes from 0 to 14. But now we've answered why, right? So 0 to 14, so that's from our KW product constant, so that's why it has that range. And then of course 7 is neutral, right? Going back from that autoionization of water and determining when our hydroxide and hydronium concentrations were equal. So see if you can figure out A. And if you need help with B, we can talk about B. So A, we could just plug in, right? So we could plug in our pH is our negative log of H plus. And I'm just writing it out so everyone can see. And so what do we get for our pH of A?
3.74. 3.7.
So 3.74 sounds good. Any questions on that one? And then how can we figure out B? I didn't tell y'all explicitly, but we had a couple of relationships.
Well, we have the hydroxide and multiplied by the H3O plus molecules. Those multiplied by equals what? 1 times 10 to the negative 4?
Negative 14,
Sorry,
yeah.
negative 14. So we can just divide with the amount of hydroxide we have to get our H3O plus.
So that's what I would do. So again, given our limited information and knowledge, that is my suggestion. So let's go do that. So 1 times 10 to the negative 14 divided by our hydroxide. And then we can find our pH of this, so negative log of our answer. So do we get about like 12.11 for our pH or so? I see thumbs up. And so now we'll learn another way to solve it. And so we can write, of course, our pH. So we can also calculate our POH. So POH is equal to our negative log of hydroxide concentration. Then, of course, we can go back and forth and so get our concentration as well. And so now we can see, so there's our pH scale going from 0 to 14. Our base scale is the exact opposite from 14 to 0, with 14 being the most acidic on our POH and 0, of course, being the most basic. And so now we have some relationships. And so this is, of course, a super useful one. And obviously, right, Trenton had just given us this relationship, right? So we knew this. But now all they've done here is take the log of both sides and just re-derived it as this expression. So, right, if we take our log, so then we just distribute this log out. So now we're just saying, well, the negative log of hydronium plus our negative log of hydroxide is equal to 14. So that gives us back out this formula here. And so this is the kind of nice thing about this chapter is at least there's a lot of ways to get your pH or POH. And so whatever one, makes the most sense and feels good at the time, just roll with that relationship. And then, of course, right, you can always plug back in and check. So it's kind of nice. Any questions about pH, POH? So now let's see how far we get into buffer solutions. And so buffer solutions are just defined as any solution that resists a change in pH when an acid or base is added. And so now we'll have to figure out how to make a buffer. And so a buffer works by neutralizing the acid or base that is added. And so how a buffer works then is that you have to have weak acid and its conjugate base. So let's just take, right, acetic acid, for instance. So if we had acetic acid, so what is the conjugate base then for acetic acid? Did you remember what that's called? What's our ion called? Yeah, acetate. So this is our acetate. But then, right, we don't just have acetate in a bottle, so it has to have a counter ion. But that means we could pick any of the appropriate ions. So sodium acetate, potassium acetate, magnesium acetate. So now we could go on and on listing off acetate salts, but that would be an appropriate combination. And so that's how you would go about determining and making your buffer. Or of course you could have a buffer of weak base and its conjugate acid. So an example that comes to mind would be, what if we picked like ammonia or something, and then that would make ammonium, right? So then we'd have to pick some sort of ammonium chloride or whatever. So that would be my first instinct. So ammonium chloride. Wouldn't want to pick ammonium fluoride though, right? Because then the fluorine can act as a base, so that would be confounding. But ammonium bromide would work. So just something that's not going to reform. And so some examples. So we have carbonic acid mixed in with our blood. Of course, right, a little bit of CO2 dissolved. And then we have, again, our hydrogen, our bicarbonate ion as the conjugate base in solution. And so again, now we can mix them. So now it's just right telling us, well, we picked acetic acid. And so like you guys came up with, we could pick sodium acetate, again, potassium acetate, lithium acetate, rubidium acetate, whatever. Just as long as we have our acetate or appropriate ion. And so a lot of this gets a little wordy. But basically, right, you can kind of see how our buffer adds. So if we add a strong base in terms of this scenario, so now reacting it with our vinegar or our acetic acid. So of course you can write your neutralization reaction. So of course it initially just makes water and then forms our acetate salt. But then part of how that buffer works, right, is then this acetate can go ahead and reform some acetic acid later in equilibrium, right? So then it goes back to our equilibrium position. And so kind of like, we said before, it gets convoluted, our wording. And so if the amount of NaOH is less than the amount of acetic acid, and so, right, this is an important part as well, is you can obviously overwhelm your buffer and just completely neutralize it out. But as long as it's less, right, the pH change will be small, and then it's kind of walking us through what's going to happen. So of course, it'll do the neutralization as shown here, and again, can reform with our base. So same thing with our strong acid. So it's showing how now the acid part reacts with our conjugate base component. So now the acid reacts with the acetate, right, makes a little bit of acetic acid, of course the salt, but then our buffer can re-equalize, right, and this could disassociate back out. So everything is always in equilibrium, and again, this leads to a small pH change, again, as long as our acid is less. And so this also goes back to Le Chatelier's principle, and again, just emphasizing that it reacts, and then it can shift back, right, to equilibrium. Blah, blah. And so good equations. So this is a useful one as kind of our shortcut. And so this is useful if we're just kind of given the components of our buffer. So usually it asks what's the pH of a buffer solution, and then we need the pKa. And then pay attention to this formula. So the way I have it written, it's a plus, and it's plus the log of base over acid, but I think your book has the other form, or maybe your notes, where pH equals pKa minus the log of acid over base. So just watch that. So I prefer this formula, but I like adding things. And so I'll think base over acid, but just be wary, right? There's going to be other forms of this equation. Henderson Hasselbalch. And so this equation is appropriate for us, again, along as the X's small approximation is valid as well. All right, I'm just trying to see what we have left in our chapter. All right, so we'll probably stop here for today. I need to double check because we didn't do too much KA, but I can't remember if that continues on to third quarter because obviously, right, you can imagine there's going to be math. So we'll probably practice that on Thursday if it's in there. Otherwise, we'll be going through this as well, so classifying our salts as acidic, basic, or neutral, and then probably looking at some titrations. All right, so grab the quizzes if you didn't grab them. So remember, they're homework. So I would start looking at them, and then on Thursday, you'll probably have maybe 15 minutes to kind of finish up collaborating, and then we'll do the trading grade in the second half on Thursday. So first hour, we'll finish up chapter 20, and then second half, we'll trade and grade. And then if you were online and wanted the quizzes, just email me so I can get you a copy early. And then otherwise, I will see you in lab for our lab practicum.